What if something could be super stable, holding onto a key component like a molecular bodyguard, and then with just the right nudge, maybe a little heat, it instantly lets go? We're talking about molecules that can both fiercely grab and readily release. Today, we're plunging into the fascinating world of some specially designed bromine-packed organic compounds.
Yeah, specifically, 2 brand new molecules called Tetrabromoazoethenes.
Ooh,
Exactly. We've been digging into a scientific paper that meticulously details how these new molecules were, built and how they behave.
Right.
Forget dusty textbooks. This is really a story about clever chemical engineering at the tiniest scale.
Okay.
And it has some really surprising results and, well, exciting possibilities for future applications.
Absolutely. So your mission, should you choose to accept it, is to join us as we explore how these intricate molecules are constructed, what makes them tick, and why they're being hailed as potential bromine carriers. That term itself is intriguing. Potential bromine carriers, by the scientists who created them. Okay, let's unpack this. What exactly are these azothenes we're talking about? What's special?
So the paper is all about creating new members of the azoethene family. These are essentially organic molecules that feature a nitrogen double bond right next to a carbon double bond. It's quite a specific structure.
Okay.
Now, the very first molecule of this type, created way back by Arens and Berndt, was quite a head-scratcher.
Really? How so?
Well, it was incredibly difficult to make. The paper mentions it yielded only a tiny 4% of the desired product. Just 4%.
Well, that's low.
It is. Yet, despite that, it was surprisingly tough. It remained stable even at a scorching 180 degrees Celsius.
Huh. Okay, 180 degrees for such a finicky molecule.
Right. Plus, the way it absorbed UV light was similar to colorful aromatic dyes, which, hinted at some unusual electronic properties.
Interesting. So what drove these researchers then? Why try and create more of these elusive azothenes?
Well, they were really interested in expanding our library, so to speak, of these unique compounds. The goal was to synthesize more examples and then compare their behavior, how they react, what their physical properties are.
Compare them to what?
To more common types of Anissa compounds, both those that are aromatic, like you find in dyes, and those that are aliphatic, which are simpler, more chain-like structures. It's really about understanding where these new molecules fit in the broader landscape of chemical compounds.
That makes perfect sense, sort of filling in the gaps in our knowledge. So how did they actually go about constructing these new tetrabromoazothenes? What was their recipe?
Their main technique was something called debromination, which, as the name suggests, is the process of removing bromine atoms.
Okay.
They started with precursor molecules called perbrominated ketazines, or PBKs for short. You can think of them as being like heavily armored with bromine atoms.
Heavily armored. I like that.
Yeah. They focused on 2 specific PBKs. One was based on acetophenone, which they called compound 2, and the other was based on propanone, labeled as compound 3.
Okay, so they began with these bromine-loaded PBKs. How did they even create those in the first place? Sounds like quite a chemical feat itself.
That's right. It's not trivial. They essentially built these PBKs by directly adding a lot of bromine to solutions of the less brominated starting materials.
Which were?
Acetophenonazine for PBK2 and acetonazine for PBK3. And they did this while the solution was heated, refluxing in methylene chloride.
And the yields for that step?
The yields for this initial bromination step were around 50%.
Okay.
Which is actually pretty good when you're trying to cram that many halogen atoms onto a molecule. It can get messy.
Right, I can imagine. All right, so we've got our heavily brominated starting materials. Now, how did they coax them into becoming the target tetrabromoazothenes? What was the magic step?
That magic step was the debromination, removing some of that bromine armor, to convert PBK2 into their first target, compound 4, which has 2 phenyl groups. Okay. They briefly heated it in a mixture of methanol, ethyl acetate, and cyclohexene. This resulted in a vibrant red compound and, importantly, in a very high yield, 70 to 75%.
Wow, that is high. Much better than the original 4%.
Definitely a huge improvement over the original azoethene synthesis. Much more efficient.
Good. And what about the second target molecule, the one derived from PBK3?
Right. The second PDK, compound 3, that one proved a bit trickier.
Why?
Mostly because it just didn't dissolve well in common solvents. Big problem in chemistry sometimes.
Yeah, solubility can be a real pain.
So to transform it into their second tetrabromoazothene, compound 5, they had to heat it in just cyclohexene for a longer time, overnight, in fact.
Overnight, okay.
And this yielded a grayish-purple compound, again with a pretty good yield, also in the 70-75% range.
Great. So now we have these two new tetrabromoazothenes, 4 and 5. The researchers mentioned that these perbrominated ketazines, the starting materials, 2 and 3, can act as bromine carriers.
Yeah.
What's the underlying idea there?
Okay, yeah. Here's where it gets really interesting, I think. They discovered that these PBKs, compounds 2 and 3, have this neat ability to readily release molecular bromine, just Br2, when you heat them up.
Like flicking a switch with temperature.
Pretty much. Think of it like that. What's even cooler is that the molecule left behind, the zoethene with fewer bromines.
Compound 4 or 5.
Exactly. That molecule can grab bromine back at room temperature, essentially regenerating the original PBK.
Whoa, so it's reversible.
It seems so. These molecules can act like reversible bromine storage and delivery systems.
That's a clever trick at the molecular level. What kind of practical uses could something like that have?
Well, the paper highlights the potential for releasing bromine in a way that doesn't involve free radicals.
Why is that important?
Because many traditional methods for adding bromine to other molecules rely on radical reactions, right? And those can sometimes lead to unwanted byproducts, less selectivity. This system, especially in solvents like methanol and possibly others that are less polar, seems to avoid that initial radical formation.
Okay, so potentially cleaner reactions.
Potentially, yes. For an efficient bromine carrier system, you really need two key features: easy release of bromine with heating, and then easy reuptake of bromine onto the resulting molecule when you cool it down or add bromine.
And how do these PBKs stack up against other systems that have been explored for, like, carrying bromine around? Are they better?
Well, other systems often involve molecules with carbon double bonds that already have other halogens attached, maybe chlorine or fluorine.
Right.
The problem there is that those existing halogens tend to make the double bond less reactive towards adding more bromine. They're electron poor, so it makes it difficult to add bromine back on.
So the regeneration step is tough.
Exactly. You often need harsh conditions like intense light, maybe UV light, to force the reaction. Plus, getting the bromine to release cleanly in the first place isn't always straightforward either.
So what makes these PBKs more promising as bromine carriers then? What's their advantage?
It seems to be a combination of factors. Firstly, having multiple bromine atoms attached to the same carbon atom, we call those geminal bromines.
Okay.
That seems to weaken the carbon-bromine bonds. Imagine trying to hold on to multiple slippery marbles in one hand. They're maybe more likely to slip away.
Right, makes sense.
Secondly, there's a lot of spatial crowding or steric strain, especially in compound 3. All those bulky bromine atoms bumping into each other put strain on the molecule, making it easier to break those CBr bonds.
Okay, weaker bonds, steric strain.
Yeah.
Anything else?
Yes. Finally, the central nitrogen double bond system, the CNNC part, is thought to play a crucial role.
How so?
It might help stabilize things during both the release and uptake of bromine, possibly by forming temporary charged intermediates. The paper mentions a structure A, for instance. We see similar charged species helping out in other reactions involving allyl compounds, so it's plausible.
Fascinating. So understanding exactly how they release the bromine is key then. The paper digs into that mechanism, right?
Absolutely. They specifically focused on how compound 2 loses bromine to become compound 4. They ran this reaction in a mixture of methanol and cyclohexene.
Okay.
And they looked closely at the products formed from the cyclohexene reacting with the released bromine species. They found they ended up with two main products, trans-1-bol-2-dibromocyclohexene and trans-1-bromo-2-methoxycyclohexene.
Right. And the significance of those products.
The key thing is the ratio of these two products. It was very similar to the ratio you'd get if you just directly added pure molecular bromine, Br2, to a mixture of cyclohexene and methanol.
Ah, okay. So the products formed give us clues about how the bromine is being released, like what form it's in.
Exactly. The similarity in the product ratios strongly suggests that a process involving charged particles and ionic reaction mechanism is at play. It implies the bromine isn't initially coming off as free radicals.
Any other evidence for that? For the ionic pathway?
Yes. Further supporting this is that they found almost no byproducts where bromine had attached to a different part of the cyclohexane molecule, like at the oleic position, specifically 3-bromocyclohexene. They found less than 1%.
And why is that important?
Because if free bromine radicals were the initial active species, you'd typically expect to see more of that type of allelic bromination product. Radical reactions often attack those positions.
Gotcha. So it doesn't seem like it's just free bromine atoms flying around, at least not initially, in this methanol mix. What's their proposed pathway involving charged particles then?
They propose an ionic mechanism where a temporary positively charged intermediate forms, which they illustrate as that structure A we mentioned.
Yeah.
But what's interesting here is that this charged intermediate doesn't seem to react with the methanol that's present in the solvent.
It doesn't, even though methanol can react with positive charges.
Apparently not in this case. Instead, the intermediate immediately gets rid of a proton to form the double bond in the final product, compound 4. It's 100% elimination.
Why would that happen?
Well, they suggest it might be due to the bulky groups around the carbon atom that would theoretically be attacked by methanol steric hindrance again, and maybe the positive charge is more stable or localized on the adjacent nitrogen atom, making elimination more favorable than addition.
That makes sense. Sometimes the shape and electronics of the molecule really dictate how it reacts. What happens when they perform this debromination of compound 2 and pure cyclohexene without any methanol around? Does the mechanism change?
Good question. In pure cyclohexene, the picture gets a bit murkier. They observed a mixture of products. About 70% was that allelic bromination product, 3-bromocyclohexene.
The one they didn't see much of in methanol.
Exactly. And about 30% was the simple addition product, 1-furphenol-2-dibromocyclohexene, where bromine just added across the double bond.
So figuring out the exact mechanism here is more complex.
It seems so. Previous work by McGrath and Tedder on the direct reaction of molecular bromine with cyclohexene also showed a similar mix of products, and they suggested a mechanism involving bromine radicals, Brom. But they also acknowledged back then that ionic pathways could potentially explain their findings too. It depends a lot on concentration and conditions.
So for the debromination of compound 2 in pure cyclohexane, it's harder to pinpoint the exact bromine-containing species that's doing the reacting?
Precisely. Just based on the product distribution, it's tough to definitively say whether the active bromine species coming off compound 2 is like a polarized form of the starting material, actual molecular bromine, Br2, or maybe a combination of both.
But the 30% addition product gives a hint.
Yes. The fact that they see 30% of the simple addition product does suggest that at least some non-radical molecular bromine is likely being formed and reacting in the expected way.
Okay. And this is definitely heat-driven, not light.
Yes. They specifically mentioned that this reaction in pure cyclohexene is a thermal process driven by heat alone. They did a control experiment which showed no reaction happening under normal room lighting over a 24-hour period.
Good to confirm. Okay, that clarifies how compound 2 behaves as a potential bromine source. What about the other PBK, compound 3? How efficiently does it release bromine?
Right, compound 3. Heating it in a specific solvent called odichlorobenzene at 150 degrees Celsius for just half an hour turned out to be a very effective way to release bromine.
How effective?
Very. They achieved an impressive 80% of the theoretical amount of bromine you could possibly get from it. They were even able to collect the released bromine gas, trap it.
Wow.
And crucially, when they cooled down the reaction mixture, they recovered the debrominated product, the octabromoazopropene compound 5.
So that clearly demonstrates that compound 3 is indeed a potent molecular bromine carrier.
Absolutely. It holds bromine, releases it efficiently on heating, and leaves behind the expected azoethene.
That sounds very practical for potential applications.
Oh.
Did they try to figure out how quickly compound 3 releases bromine? Like the kinetics?
They did attempt to study the rate, yeah. They looked at the kinetics of bromine loss in a mixture of odichlorobenzene and another chemical called 1-octene at 108 degrees Celsius.
Oh, yeah.
Unfortunately, this experiment got complicated. It seems other colored compounds started forming, likely from further reactions of the product, compound 5, maybe breaking down or reacting with the octene.
Side reactions messing things up.
Happens all the time. But by using UV spectroscopy to monitor the disappearance of compound 3, they were able to get an estimate. They reckon that about half of the bromine would be released in roughly 30 minutes at that temperature, 108 degrees.
Okay, so a reasonably fast release at that temperature. Now, shifting gears slightly, how do these newly created azokenes themselves, compounds 4 and 5, how do they react when they encounter bromine and other halogens? Can they take bromine back easily?
Yes, so both azokenes 4 and 5 react completely quantitatively with bromine in a solvent called methylene chloride at room temperature.
Oh, so the reverse reaction works well.
It does. Compound 4, the diphenyl one, reacts almost instantly. Zap, it's done.
And compound 5?
Compound 5, the really crowded one, takes a bit longer, about 30 minutes to fully react.
Any idea why it's slower?
It might be due to that steric hindrance we talked about. The crowded arrangement of atoms around its double bonds makes it harder for bromine to approach, and also its lower solubility probably doesn't help either.
Makes sense. What about other halogens? Do they react with chlorine or iodine?
Interestingly, compound 4 showed absolutely no reaction with chlorine gas or with iodine when they were mixed in methylene chloride at room temperature.
Huh. That's quite selective. Only bromine. Why do you think it's so picky about which halogen it reacts with?
Well, the lack of reaction with chlorine is likely due to a less favorable electronic interaction.
Hmm.
The double bonds in compound 4 are already electron poor because of all the bromines attached nearby.
Right.
And chlorine is also quite electron hungry and electrophile. So maybe there isn't enough driving force for them to react easily, like repelling, like almost.
Okay. And iodine. Why not iodine?
For iodine, it's probably a combination of things. Again, those bulky groups around the double bond, making it physically difficult for the larger iodine molecule to approach steric hindrance, and also maybe thermodynamics play a role. The addition of iodine across double bonds is often less favorable than bromine or chlorine, and it might even be a reversible process at room temperature favoring the starting material.
Fascinating selectivity. Now, the paper also describes a rather intriguing molecular rearrangement that happens to one of these azoethenes when heated. Tell me more about that.
Yes, this was a really fascinating and, I think, unexpected discovery for them. They noticed first that the way both Tetrabromoazoethenes, 4 and 5, absorb UV light was quite similar to that of aromatic azo compounds, like the ones used in dyes.
Okay.
But then, when they heated azoethane 4 in a solvent chlorobenzene, it completely
Transformed into what?
into a totally different molecule. A colorless, crystalline product, which they figured out has a slightly different arrangement of atoms. They called this new structure compound 6, identified as 2-aza-3-phenyl 1,1,line-4-tetrabromo-1-bol-3-butadiene. Quite a mouthful.
Whoa, okay. So a significant change in both structure and appearance going from red to colorless. Was this rearrangement specific to compound 4?
Well, interestingly, they found that they could also get the same rearranged product, compound 6, by simply heating compound 3, the perbrominated precursor, on its own, neat to 190 degrees Celsius.
Really? Heating the starting material gives the rearranged product of compound 4.
Yes, but in that case, it was accompanied by decomposition and the formation of another molecule called benzonitrile, PHCN, so it wasn't as clean.
How did they confirm the structure of this rearranged compound 6?
They used standard spectroscopic techniques like infrared IR and nuclear magnetic resonance NMR spectroscopy. The data, particularly the frequencies for the carbon-nitrogen and carbon-carbon double bonds in the IR spectrum, supported the proposed structure of 6.
Do they have any ideas about how this molecular reshuffling, this rearrangement, might actually be occurring? What's the mechanism?
They suggest a possible mechanism. It might involve the molecule first sort of folding up on itself in a specific way, what chemists call a corrodatory ring closure, to form a temporary ring-like intermediate, which then opens up differently to give compound 6.
Complex. Did they measure how fast it happens?
They did. They measured the rate of this conversion of 4 to 6 at 119 degrees Celsius in chlorobenzene and found it follows first-order kinetics with a specific rate constant.
What about the stability of compound 4 itself? You said it rearranged when heated in solution. What if you just heat it neat?
Good point. They found that azothane 4 is actually stable when heated neat on its own up to 190 degrees Celsius.
So it needs the solvent somehow. Or maybe just higher temps break it down.
Well, it does decompose if you heat it higher to 220 degrees Celsius. But interestingly, when it decomposed, they looked for a specific fragment in dibromoacetone trial, which you might expect based on the structure, but they didn't find any among the breakdown products.
More chemical mysteries. This has been a really deep dive into some very specific and, frankly, complex chemistry around these azoethenes.
It certainly has.
Now, the main focus of the paper is clearly these tetrabromoazoethenes, but the notes you shared, based on the source text, briefly mentioned something else at the end, something about creating esters of glutamic and aspartic acid. How does that relate?
Right. That appears to be a separate but perhaps related in terms of illustrating chemical control piece of research also included in the document source. It's not directly about the azoethenes.
Okay, so what's it about?
It highlights another example of chemists carefully manipulating molecules to achieve a specific outcome. It describes a new and apparently efficient method for creating specific versions of common amino acids, glutamic and aspartic acid, specifically making what are called monoesters.
Monoesters.
Yeah, where only one of the acid groups is converted to an ester. They used a copper-based catalyst to selectively break apart related molecules called diesters, where both acid groups are protected as esters.
Why is that useful?
Well, this kind of selective protection and deprotection is really important in the field of peptide synthesis making proteins. You often need to protect certain parts of amino acids while you modify other parts.
I see.
Benzyl esters are commonly used for this protection, but the paper notes they can sometimes be too stable, hard to remove selectively. This new copper-catalyzed method offers a way to precisely remove just one of the protecting groups, the ester groups, in high yield.
Any specific examples?
Yeah, they show how to convert glutamic acid to benzyl ester, where both ends are protected specifically into its gamma benzyl ester, leaving the other end free.
So while it might seem different from the azoethane chemistry,
Exactly. It's another illustration of the ongoing effort in chemistry to develop precise tools for building and modifying molecules for specific purposes. Just a different application area.
okay, that makes sense. Let's try and bring it all together then. What are the key insights that you think our listeners should take away from this deep dive into these bromine-containing compounds, mainly the azoethenes?
Well, I think the big picture here is the successful creation and really detailed study of these two novel Tetrabromoazoethenes. They exhibit some truly remarkable properties.
Like the bromine carrier idea?
Exactly. Their potential to act as bromine carriers, especially the way they can release bromine potentially without forming radicals under certain conditions, that's really intriguing. It could lead to cleaner, more selective chemical reactions.
Right. And the mechanism clues?
Yeah, we saw evidence pointing towards an ionic mechanism for bromine release in one case in that methanol mixture, and the very efficient generation of just plain molecular bromine from the other precursor, compound 3, upon heating.
It's a rearrangement.
And let's not forget that surprising ability of compound 4 to completely rearrange its structure when heated. That reveals unexpected chemical pathways and just shows how complex these systems can be.
So the real aha moment for me is how these molecules, which, appear quite stable on the surface, can undergo these dramatic transformations depending on their surroundings, heat, solvent. Right. And studying that gives us a deeper understanding of how chemical reactions actually happen at the molecular level, while also hinting at potential real-world applications, like maybe more controlled ways to introduce bromine into other molecules.
Exactly right. And it really makes you think about the power of molecular design, doesn't it? Chemists are constantly striving to create molecules with specific functions, and these bromine carriers and the observed rearrangements are, I think, great examples of that ongoing quest. It's about control at the nanoscale.
So the final question to ponder then, maybe for our listeners, could these bromine carriers pave the way for entirely new and more selective methods in organic synthesis, or perhaps even inspire the creation of novel materials with built-in reactivity?
It's possible.
And maybe what other seemingly stable molecules out there might possess hidden reactivity, just waiting for the right trigger, the right conditions to be discovered.
It's a fascinating world down there at the molecular level.
Constantly full of surprises.